In this video, we're going to take a look at the arc length function idea that we talked about in the last video and see how we can actually use it to do something new and interesting with some of our vector functions. So as I state here at the next part in the notes, in pretty much all of the previous sections, we've thought about our vector functions as having an input variable of a t. So that t we thought of as time, and so we could imagine that as we moved along a curve out in space, regardless of what it was, oops, it's not letting me draw all the way there, but all right, so as we moved along a curve out in space, we could think about being at any point on that curve was really associated with some value of t. But on occasion, it might actually be useful to not just try to focus on where I am on the curve with respect to the variable of time, but maybe with respect to something else. And one of the things that we're going to focus on right now is if I had a specific starting point, okay, which I'll indicate by this black dot here, could I measure where I am along the curve? Not by how long it takes me to arrive there, so to speak, but maybe by how much distance was covered in order to arrive at that point. Take a look down here at the following definition. Suppose we have a curve C, it's a vector function defined on some interval from A to B. We have a smooth vector function, it's traced exactly once, so it's ready to have an arc length calculated for it. If it's the case that the arc length function for C can be solved for t, that is, I could go back and rewrite that function, which remember usually was s of t equals stuff with t. If I could rewrite that function to instead say t equals stuff with s, if I could kind of flip that, then it would be possible to say at all of the t's in my original function, I could replace them with this new stuff with s formula, and I could kind of re-express my vector function without a variable t, but instead with a variable of s. And since s measures the length along the curve, I will have done exactly what I talked about up here in the picture. I will have said, based on a starting point, I can navigate to any other point by talking about how far along the curve I will traverse. So in general, this is kind of the way that we're going to go through these problems. Okay? If I wanted to find an arc length parameterization of a curve, then I would start by getting s of t, get the arc length function. I would then try to do what I wrote up here, which is solve that resulting arc length function to get it to say t equals a bunch of stuff with s. And then I can take that in step 3 and substitute that s formula, or that formula with s's, I should say, into my r of t function. Okay. Again, the nice thing about doing this is it lets me say that if this right here represents my start point, instead of saying that I'm going to measure a time, I could measure a distance. So that way I could go to my function and say, hey, where would I be after I've moved 2 units along the curve? And my vector function would then say, you would be right here at this final point. It would point me to that new point. So let's take a look at how this works with a specific example. Here down in example 3, again, I'm working with the same vector function as before. I want to find the arc length parameterization. Okay, so the first thing is I would need to be able to find the s of t for this function. Now fortunately, we already found this back in a previous example. We found this to be square root of 5 times t. This was from example 2. Okay. So now the question would be, could I go ahead and actually solve this for t? Well, yeah, that's actually unbelievably simple. You'll note that if I just divide both sides by a square root of 5, I get t equals s over root 5. So I've now rewritten t, and I have a formula that contains only s's. Well, now that means I could actually go to my r of t formula, and I can turn it into an r of s formula. Okay, so I'm going to write it here as like r of s, because I can go and say, well, if t is just equivalent to s over root 5, then I should be able to rewrite this as cosine of 2 s's over root 5 and sine of 2 s's over root 5, and then finally just s over root 5. Okay. So this would allow me to, again, be able to redefine what this curve actually is. I've created an arc length parameterization. So if you take a look at part B, then now I could ask some questions like, okay, so if I wanted to now move along this curve 1 unit or 2 units, I could just plug in the associated number. So take a look here. Where would this function tell me that I would be located in space if I decided to move this distance along my curve? Okay, well, let's actually see what that would look like. If I went to my function and I plugged in square root 5 pi over 2, let's see what that would create. So I would have cosine of, and you'll notice that when I plug this in here for the value of s, that's going to make the 2 and the root 5 cancel, and I'm just going to be left with pi. Similarly, I'm going to be left with sine of pi, and at the very end, I'll be left with simply pi over 2. So if I clean this up, I'll note that cosine of pi is -1, sine of pi is 0, and my final component is pi over 2. What this tells me is that on my helix function that started down at 1, 0, 0, and remember it kind of went out and around like this, right? And just kind of kept rotating up and up and up. This was, what my curve here actually looked like. We said that after I've moved this specific distance along the curve, my function now is spitting out the point. It says, hey, you stopped right here. You stopped at the point -1, 0, pi over 2. And that should actually make perfect sense to us as to why I've landed at that point. Because take a look back at our previous examples. We saw actually back in example number 1 that the total length of the curve from 0 to pi over 2 was this distance. And that was when I went from 1, 0, 0 all the way to, there it is, the point -1, 0, pi over 2. So of course, since I originally was moving this length to go from the first point to the second, then when I ask the arc length parameterization to start here and move this distance, I should land at the exact same point. There's no surprise there actually whatsoever. So this is kind of one of the advantages of being able to kind of reparameterize or rewrite one of our functions here. Okay? And on occasion, we may need to do this for certain applications. And we'll talk more about that in later videos in the semester.